Okay, today we are discussing an important topic called maximum and minimum of functions of two variables. Here we are studying some applications of the concept of partial derivatives. And I have already studied maximum and minimum of functions of function of one variable, single variable calculus. It is just an extension to two variables. And you know that in one variable calculus, suppose we are dealing with a function of the form y is equal to fx. The geometry of that y is equal to fx is a curve drawn on a plane. And here we are discussing the function z is equal, for example, z is equal to some function of x comma y. And that z is equal to f of x comma y is a 3D surface, you know. And here we are, first of all, we are discussing what is a surface. The surface is given by the equation z of xy, or f is equal to x square plus y square, or f of x comma y is equal to x square plus y square. What is the name of the surface? Rotating that parabola about one axis. For example, suppose we are rotating that parabola about a y-axis.
Paraboloid.
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 Okay, good. That means if you are rotating that parabola y is equal to x square about the y-axis, a surface is generated, 3D surface is generated, and that surface is called paraboloid. Here the axis of that paraboloid is z-axis. Here the red indicates x-axis, green is the y-axis direction, and blue is the z-axis direction. So we can have the paraboloid surface. And if you are inverting that paraboloid and shifting one unit above the xy plane, we get another surface. So this is also a paraboloid. Some portion of that paraboloid lies above the xy plane. And see another one. What is the name of this surface? See, this is the equation f of x comma y, or z is equal to square root of x square plus y square.
On.
And say another surface. Say this surface is generated by the equation z of xy is equal to cos x into sin y. This is the graph of cos x into sin y. See, in all these cases, we have seen certain surfaces, and that surfaces have some, at some point, the value of the function highlighted above the xy plane, or at some points below the xy plane. Okay, and these points are called the local maxima and local minima. If in our portion, that means maximum and minimum functions of two variable, we are looking for that points, such points, at which point the function has a local maxima, at which point it has local minima. If the function is defined in some region, say the domain is given, we are computing all such a possible local maxima and local minima. And out of that local maximum and local minima, we have to choose the maximum value, that is called the absolute maximum. And out of the minimum values, we take the lowest one, that is called the absolute minimum. And that concept of absolute maxima and absolute minima, we can define only when the domain is given. And whenever that domain is a closed and bounded set, then only we can have the concept of absolute maxima and absolute minima. Okay, clear? For this indicated surface, say the surface given by the equation, can you say what is the local maxima or local minima of this function? We can say about the local minima. What is the local minimum, local minima of the function? What is the minimum value of this function?
0
Zero.
The minimum value is 0, and that minimum value 0 can occur at which point?
origin.
So this function, what is the equation of that function? Equation is z is equal to, or f of x comma y is equal to x square plus y square. That is a paraboloid surface, and that paraboloid surface can have exactly one minimum, and that minimum value can occur at origin 0 0, and that point is called a local minima. And what is the function value in the neighborhood of that origin as compared to the value at 0 0? This is the shape of that function. This is the surface generated by the equation z is equal to x square plus y square. And for this function, we are looking for its minimum value and maximum value, whether it is possible to determine the minimum value or the maximum value. Okay, if the function is defined in a closed and bounded set, then you can find out its minimum value and maximum value throughout the region. Okay, otherwise, we can locate some points where the function can have the lowest value. At some points, it can have the highest value. and that points are called relative maxima and relative minima. And for this indicated graph, the graph of the function given by f of xy is equal to x square plus y square, it can have a local minima at the origin, and the minimum value is equal to 0. And my question is, in the neighborhood of origin, we are evaluating the function, and we are evaluating the function at the origin also. Then compare the values of the function at origin with the values of the function in the neighborhood of the origin. What will be the inequality? If I am taking a point in the neighborhood of origin as x comma y, then compare the values given by f of x comma y and f of 0, 0. What will be the inequality?
F of 0
F of 0, 0 will be
great.
less than
or equal to
f of x comma y for all xy in the given domain, okay, or for all xy in the circular disk centered about the origin. And that point, the corresponding point 0, 0 is called a relative minima, okay. And similarly, if you are considering another function, we are shifting down, that means we are inverting this paraboloid surface. Suppose by we are taking instead of fxy is equal to x square plus y square, if the function is fxy is equal to minus s square minus y square, this paraboloid surface will be inverted. And I am lifting that inverted paraboloid surface 1 unit above the xy plane. We get the equation like this. This will be the equation. Equation of the paraboloid surface is 1 minus of x square plus y square, or 1 minus s square minus y square. And for this function, what are the local maxima or local minima? So this, what is the highest value of the function?
1.
Highest value is 1, and that highest value is occurring at which point? Origin. Okay. And as before, again we are comparing the value of the function at origin, because at the origin it can have a maximum value. From the diagram, from the graph, it is directly visible. So we are comparing the values of the function at origin with the values of the function in the neighborhood of origin. We are taking some points in a circular disk centered about the origin. And if you are taking some point in the neighborhood of origin as x comma y, and we are comparing the value of f of x comma y with f of 0, 0. Here we can see that all the function values in the neighborhood of origin, that means f of x comma y should be less than or equal to f of 0, 0 in the disk, circular disk centered about the origin. So this inequality is satisfied. We say that the function has a local local maxima at the point 0, 0. So the point 0, 0 for this function is acting like a local maxima, and the origin, the same origin, is acting like a relative minima for the function paraboloid surface. It is a relative maxima for the inverted paraboloid lifted 1 unit above the xy plane. And similarly, if you are considering the conical shaped surface given by f of x comma y is equal to square root of x square plus y square, again we can say that origin is acting like a relative maxima or relative minima. For this conical surface, it is a relative minima, because we can see that in the neighborhood of origin, if we take any point, say x comma y, and we are evaluating f of x comma y and comparing that f of x comma y with f of 0, 0, we can see that this f of x comma y values are greater than or equal to f of 0, 0. So we say that the function has a relative minima at the origin. And see the next figure. The surface given by this equation, f of x comma y is equal to cos x into sin y. And for this function, fx is equal to cos x into sin y, how many relative maxima and relative minima are possible? For the previously discussed surfaces, we can have exactly one. For the first graph, it can have exactly one relative minima. For the second graph, it can have exactly one relative maxima. And for the third one, it can have exactly one relative minima. And for this surface, how many such relative minima or relative maxima are possible?
Infinite.
It can have infinitely many relative maxima and relative minima are possible. Suppose we are cutting that surface using some boundary okay, including that boundary point also, then we can have finite number of relative maxima and relative minima. Out of the finite number of relative maxima and relative minima, suppose we are taking the highest values of all possible relative maxima, that highest value is called the absolute maxima. Okay, and similarly for out of all relative minimas, we are taking the lowest one, that is called the absolute minima. And in our portion, we are going to discuss under what condition we can expect a relative maxima or a relative minima. At the relative maxima and relative minima, what are the specialities of that points? For which type of functions that type of relative maxima and relative minima can occur? What are the computational procedures? Okay, so these are the things we are going to discuss in this class. So first of all, we have the definition, relative maxima and relative minima, absolute maxima, absolute minima. A function of two variable is said to have a relative maximum at a point x0, y0 if there is a disk centered at x0, y0 such that f of x0, y0 should be greater than or equal to f of x, comma y for all points xy that lie inside the disk. And f is said to have an absolute maximum at x0, y0 if f of x0, y0 greater than or equal to fxy for all points xy in the domain of f. So these are the definitions of relative maxima and absolute maxima. For relative maxima, the inequality is satisfied in the neighborhood of x0, y0. For absolute maxima, that inequality must hold for all possible points in the domain. And similarly, we can have the definition of relative minima and absolute minima. For relative minima, the inequality f of x0, y0 should be less than or equal to f of x, comma y in the neighborhood of the point. And for absolute minimum, this inequality must hold for all points in the given domain. So you have to note all such definitions of relative maxima, absolute maxima, relative minima, absolute minima. Then we are going to discuss under what conditions we can expect such a relative minima and a relative maxima. And for a function, that means this is called extreme value theorem. If f of x comma y is continuous on a closed and bounded set R, then f has both an absolute maximum and an absolute minimum on R. This is the existence theorem. Whenever the function is defined in a closed and bounded set, then we can have some absolute maxima and absolute minima. So why we are stressing the point, the domain should be closed and bounded. Otherwise, what happens? Suppose we are defining a function in an open set. See the simple case of one variable case. Suppose I am considering the function, say the parabola y is equal to x square. Suppose the parabola is defined in an open interval minus 2 to 2. In open interval minus 2 to 2, what is the local minimum of that function? Y equal to x square.
0.
Local minima 0. Any local maxima is there?
4.
The function is defined in open interval minus 2 to 2. The value 4 will occur exactly at the point x equal to minus 2 or x equal to 2. Right?
ഓൾമോസ്റ്റ് 4ന്റെ അടുത്തായിട്ടല്ലേ വാല്യൂ വരും?
അപ്പൊ നമുക്ക് അതിനെ എടുക്കാൻ പറ്റൂല. അതൊരു നമുക്കൊരു പോയിന്റ് എടുത്തു കഴിഞ്ഞാൽ വി കനോട്ട് കമ്പ്യൂട്ട് ദി അബ്സല്യൂട്ട് മാക്സിമ. ലോക്കൽ അല്ല ചോദിച്ചേ, അബ്സല്യൂട്ട്. So the function can have some absolute minima in the interval minus 2 to 2, but it cannot have absolute maximum. The absolute maximum can occur at the exact point, say x equal to minus 2 and x equal to plus 2. But if instead of that open interval minus 2 to 2, if you are considering the closed interval minus 2 to 2, then the function should have some absolute maximum and absolute minimum. This is what is called extreme value theorem. If you are extending this concept for a two variable function, the domain is not an interval, the domain is a subset of the plane. Here the subset of xy plane. In the subset of the xy plane, if you are considering a region having boundary, the closed boundary means the region which is inclusive of all the boundary points. For in the closed and bounded disk, the boundary points are also included. If you are defining a function in such a closed and bounded set, that means the boundary points included, then we can expect some absolute maxima and absolute minima provided the function is a continuous function. Clear? So that is the main point. That is the main theorem which we are depending on for existence of an absolute maxima and absolute minima, not for local maxima and local minima. The extreme value theorem says that if the function is a continuous function on a closed and bounded sets, see, not the two conditions. First condition is the function must be continuous. Okay, the function is continuous, and the second one is the function is defined in a closed and bounded set. Closed and bounded set in the region. Closed and bounded set in the domain. Then f has an absolute maximum and an absolute minimum on the corresponding region R. That is the existence theorem. Then how to find that relative maxima and relative minima? Where to locate the relative maxima and relative minima? If f has a relative extrema, relative maxima and relative minima, that two words are combinedly called relative extrema. If f has a relative extremum at a point x0, y0, and if the first order partial derivatives of f exists at that point, then we can see that the first partial derivative fx evaluated at that point will be 0. First partial derivative of the function in the y direction evaluated at that point will be 0. So that is a condition for existence of relative extrema, whether it is a relative maxima or relative minima. And if the first order partial derivatives exist, then only you can have the condition the first order partial derivatives at that points are zeros. So what happens if the first order partial derivative does not exist? See the figure. The paraboloid z is equal to, or f of x comma y is equal to x square plus y square. What are the first order partial derivatives? See the first order partial derivatives of this function x square plus y square.
2x and 2y.
2x and 2y. What are the values of 2x and 2y at origin? 0.
0.
Okay.
0.
So first order partial derivatives are 0 for this function. See the function. The function can have the first order partial derivatives at a 0. And this is a continuous function. So the first order partial derivatives exist. No condition for existence. So the first order partial derivatives exist. So we can expect one local maxima or local minima at the point origin. Similarly for the second surface. For the second surface also, the first order partial derivatives are, what is the second function? Inverted paraboloid lifted 1 unit above the xy plane. The equation is 1 minus x square minus y square. And as before, here also we can have the fx, first order partial derivatives with respect to x, minus 2x, another derivative, minus 2y. And if you are evaluating these two derivatives at origin, the values are 0, 0. And so we can expect some relative local maxima or local minima at the point. See, what about this function? Can you find the there is a sharp corner at that point. Okay, if you are trying to find out the first order partial derivative fx, we will get to the answer 1 by 2 root. The equation is z of x comma y, or fxy is equal to square root of x square plus y square. Square root of x square plus y square have the derivative. What is the derivative? 1 by 2 root of x square plus y square into 2x. Or simplified answer is x by root of x square plus y square. And if you are trying to evaluate that derivative at the origin, we will left with an indeterminate form. That means the limit does not exist. 0 by 0. Okay. So the first order partial derivatives does not exist at this point origin. And other than that origin, we can have some first order partial derivatives. But at the point origin, this function, that means square root of x square plus y square, does not have the first order partial derivative. But the function can have a local minima. From the diagram, it is clear that the function can have a local minimum at that point. So what are the conditions? So we have to extend the definition of existence of a relative extrema at a point. So one condition is if the first order partial derivatives exist, then all the derivatives, first order partial derivatives must be 0 at the relative extremum point. And another point is if a relative extremum exists at the point x0, y0, it does not imply that all the first order partial derivatives must be 0. So we have to look for a general definition, and that is called a critical point. A point x0, y0 in the domain of the function fxy is called a critical point of the domain, a critical point of the function if the first order partial derivatives are 0 or if one or both partial derivatives do not exist at that point. So we have to account for all the points at which first order partial derivative is equal to 0, and we have to consider the points at which first order partial derivatives may not exist. The derivative, the first derivative in the direction, that means the derivative in the x direction may not exist, or the derivative in the y direction may not exist, or both the derivatives may not exist at the point x0, y0. Then we have to consider that point also for checking at that point whether there is some relative maxima or relative minima. And collectively, all these points are called critical points. Okay, then how can you define a critical point? A critical point is a point at which either the first order partial derivatives are zeros, or if the point at which one or both of the first order partial derivatives does not exist. So that point is called a critical point. So in order to find the relative extrema or relative maxima or relative minima of a function, we have to, first of all, we have to consider the critical points of that function. See the example for the function z is equal to x square plus y square. The first derivatives are zeros at the origin. So both the function can have relative and absolute minimum at 0, 0. Here also the derivative is 0. It can have relative and absolute maximum at 0, 0. For this function does not exist. That means the first derivative does not exist. But it can have some relative and absolute minimum at 0. So we have to consider another point. A function of two variable need not have a relative extremum at a very critical point. That is another idea. So first of all, we have seen that at a critical point, the function can have some relative extremum. But the converse is that a function of two variable need not have a relative extremum at a very critical point. Okay, if the function can have a relative extremum, then the point is a critical point, but the converse need not be true. All critical point does not give a relative maximum or a relative minimum. Why? See the function z is equal to y square minus x square. See the graph of this function. See, this is the graph of the function z is equal to y square minus x square. This surface is called hyperbolic paraboloid. For this function, at origin, can you see some relative maxima or relative minima? What are the possible first order partial derivatives? Y square minus x square. What are the derivatives?
2y minus
2y
2x.
minus 2.
Minus 2x and plus 2y. Okay. And if you are evaluating that derivative at origin, we will get the answers 0. 0 for the partial derivative in the x direction, 0 for the partial derivative in the y direction. So that point corresponds to a critical point, because a point at which derivative vanishes is called a critical point. A point at which derivative does not exist is also called a critical point. Here the derivative exists, but at this critical point, we cannot have a relative maximum or relative minimum. Why? Suppose we are considering this graph, we are taking a cross section. Suppose we are cutting this surface using a plane, or if you are cutting this surface using the plane, what is a plane? The plane is YZ plane. See the cross section will be in the form of a parabola. Okay, for this parabola, this origin is acting like a relative
Minima.
relative minimum. So in the opposite direction, suppose I am rotating this graph in the opposite direction. Now what are the axes? The axes are red and blue. Red and blue means XZ plane. In the XZ plane, what is the cross section? Cross section of the surface in the XZ plane. That cross section will be, the cross section will be in the form of Inverted parabola. For the inverted parabola, origin is acting like a relative
Local maximum.
relative maximum, local maximum. See, if you are viewing that surface in two directions, in one direction, we can say that it is acting like a local maxima. In another direction, if you are viewing the same surface at the same point, it is acting like a local maxima. Such points are called as saddle points. So we cannot consider that point as either a relative maxima or a relative minima, because in two different curves, that means if you take the cross section of the same surface in two different planes, the corresponding curves, that means the curves lies on the cutting plane will have some relative maxima, local maxima and local minima at the same point. So that point is called a saddle point. Clear? We cannot consider that point as a local maxima or local minima. Such points are called saddle points.